What if we took every nuclear weapon ever built by human hands and aimed them, one by one, at every world in our solar system? Not just dropped them, studied them, watched what happened. Because the answer is not what you think. And in some cases, it's genuinely terrifying. Here's the thing that nobody talks about when they imagine blowing up a planet. The most powerful weapons in human history, the things we built specifically to erase cities, to end civilizations, to poison the sky for generations, are, compared to the cosmos, almost embarrassingly small. And yet, on some worlds, a single nuclear detonation would do something so bizarre, so unexpected, so downright strange, that it redefines what we thought we knew about both physics and the universe we live in. We're going to nuke every planet. We're going to follow the science wherever it goes. And by the end, you're going to look at the night sky completely differently. Let's start at the beginning. Mercury. Mercury is the smallest planet in the solar system, and it is basically a rock with an iron core the size of our moon wrapped inside it, and absolutely zero atmosphere to speak of. Which means that the moment you detonate a nuclear weapon on its surface, everything we instinctively know about nuclear explosions goes out the window. On Earth, the terrifying power of a nuclear weapon comes largely from what it does to the air around it. The energy superheats the atmosphere to tens of millions of degrees, generates a crushing pressure wave, and throws out thermal radiation in every direction. That combination is what flattens buildings, ignites firestorms, and kills at distances of dozens of kilometers. Mercury has none of that. No air means no pressure wave. No pressure wave means no shock wave. And no shock wave means no iconic mushroom cloud rising into the sky. Instead, roughly 80% of the energy releases silently. A burst of X-rays and gamma radiation that slams into the surface and vaporizes the top layer of rock in a fraction of a second. The remaining energy transfers directly into the planet as seismic force. And here is where Mercury gets genuinely interesting. Because Mercury is small, dense, and rigid, more like a colossal metal bell than a planet, it doesn't absorb that seismic energy. It rings. A 50-megaton detonation, the largest ever tested by humans, would send seismic waves rippling all the way around the planet, bouncing off the interior and converging at the exact antipodal point, the spot on the opposite side of Mercury from the blast. At that point, the focused seismic energy could shatter the crust, trigger landslides, and send enormous chunks of Mercury spraying into space. Some of those chunks would end up on an orbital path toward Venus, which is convenient because that's exactly where we're headed next. Venus is, in almost every measurable sense, the opposite of Mercury. Mercury has no atmosphere. Venus has an atmosphere so thick, so dense, so crushingly heavy that standing on its surface would feel like being submerged 920 meters underwater. The atmospheric pressure at the Venusian surface is 92 times that of Earth at sea level. And the temperature? A permanent 465 degrees Celsius, day and night, pole to pole. Venus is not a planet that plays nicely, and a nuclear weapon detonated there would quickly discover that. In 1955, the United States actually tested something roughly comparable. Operation Wigwam detonated a 30-kiloton atomic bomb several hundred meters underwater in the Pacific Ocean to study what would happen to submarines. The results were violent, contained, and deeply strange. The water around the explosion behaved like a physical wall, crushing the blast back into itself. Now imagine that, but with an atmosphere 92 times denser than Earth's, stretching 100 kilometers above the surface. A thermonuclear weapon detonated on Venus would create a flash of plasma, a superheated bubble of ionized gas that would be compressed almost instantly by the surrounding atmospheric pressure. The blast radius would be a fraction of what it would be on Earth. The explosion would be, in the most bizarre way possible, throttled by the planet itself. Venus's atmosphere is already so hot and so energetic that even our largest fusion bombs would add less than a rounding error to its global temperature. It would be like throwing a lit match into the heart of a blast furnace. From orbit, through Venus's permanently cloud-covered sky, you'd barely see a flicker. The planet would swallow the bomb whole and not even notice. Now, let's talk about Mars, which is the planet people actually want to nuke. Not out of hostility, out of optimism. The idea has been floated by serious scientists and not-so-serious tech billionaires alike. Detonate nuclear weapons over the Martian poles, vaporize the frozen carbon dioxide in the ice caps, trigger a greenhouse effect, and jumpstart the process of terraforming. It sounds logical until you actually run the numbers and watch the plan collapse. A Tsar Bomba-scale detonation near a Martian pole would not warm the planet. It would cool it. Mars's atmosphere is already razor-thin, less than 1% the density of Earth's, but it is thick enough to carry dust. A nuclear explosion powerful enough to make any real impact on the ice caps would simultaneously kick up an enormous dust cloud into the upper atmosphere, blocking sunlight and triggering a localized nuclear winter. You'd make Mars colder, and you'd destroy something irreplaceable in the process. The Martian polar ice caps are geological time capsules containing hundreds of millions of years of climate data and possibly complex organic chemistry that could hold clues about ancient microbial life. A nuclear strike would vaporize that record forever, in exchange for making the planet slightly worse. You'd also almost certainly kill every rover currently operating on the surface. And we love the rovers. So let's not do that. Jupiter. Jupiter is where nukes go to feel completely insignificant. This planet is so massive it contains more than twice the mass of every other planet in the solar system combined. It has no solid surface. Its atmosphere is thousands of kilometers deep, transitioning gradually from gas to liquid to a crushing metallic hydrogen interior where the pressure exceeds anything we can produce in a laboratory. Detonating every nuclear weapon ever built by humanity, all 12,000 plus warheads, simultaneously inside Jupiter's atmosphere would produce a temporary hot bubble in the upper cloud layers. A localized thermal event. And then, within seconds, Jupiter's storms. Winds moving at over 600 kilometers per hour, systems larger than the entire Earth, would simply close over the explosion like water closing over a stone. You wouldn't even see it from orbit. We know this because in July of 1994, we actually watched something hit Jupiter with the equivalent force of 300 million nuclear weapons. Comet Shoemaker-Levy 9 had broken apart into 21 separate fragments, and over the course of 6 days, every single one of them slammed into Jupiter at 60 kilometers per second. The impacts sent plumes 3,000 kilometers into the atmosphere, heated the local environment to 40,000 degrees Celsius, and left dark scars visible from Earth for months. And Jupiter noticed about as much as an ocean notices a raindrop. The scars faded. The storms rolled on. Jupiter just kept going, because that is what Jupiter does. To actually destroy Jupiter, to produce enough energy to permanently overcome its gravitational binding energy and blow its mass into space, you would need approximately 100 quadrillion times the entire combined nuclear arsenal of Earth detonated simultaneously at its core. The core sits at pressures of hundreds of millions of pounds per square inch and temperatures around 24,000 degrees Celsius. You would need a delivery vehicle that cannot be built, carrying a number of warheads that cannot be manufactured, in a time frame that cannot be achieved. Jupiter is not a planet you destroy. Jupiter is a planet that destroys things. Saturn is essentially Jupiter's slightly smaller impossibly more beautiful cousin, and the nuclear physics work out the same way. Detonate anything in its atmosphere, and the planet absorbs it without comment. But Saturn gives us something Jupiter does not: the rings. And nuking Saturn's rings is genuinely one of the most interesting things you can do with a nuclear weapon in this solar system. Saturn's rings are not solid. They are a trillion individual chunks of ice and rock, ranging in size from dust grains to objects as large as houses, all orbiting in a disk that stretches 280,000 kilometers from the planet, but is less than a kilometer thick in most places. A nuclear detonation inside the rings would do something spectacular. The explosion would vaporize ice, create a superheated plasma shockwave, and blast a hole through the disk. Ionized particles would be captured by Saturn's powerful magnetic field and either swept down into the planet's atmosphere or hurled out into space. It would look extraordinary, and then, within days, the gap would close. The rings are a dynamic, self-organizing system, and the surrounding material would simply drift back in and fill the space. Saturn's rings would heal themselves. Because the universe is surprisingly good at healing itself when given enough time. Uranus is next, and Uranus is where things get genuinely surreal. Uranus is an ice giant. Its interior is rich in water, ammonia, and methane existing in exotic, high-pressure states that have no parallel on Earth. Detonate a powerful thermonuclear weapon deep in the methane-rich layers of Uranus's mantle, and the shockwave would do something no weapon has ever done anywhere on Earth. The intense pressure and energy would snap methane molecules apart, liberating the carbon atoms inside. And under the crushing pressures of the Uranian interior, those liberated carbon atoms would compress and crystallize. The explosion would produce diamonds, not a metaphor, actual solid diamonds, raining through the atmosphere. Recent research from 2022 and 2023 conducted using high-powered lasers at the National Ignition Facility confirmed that this process, diamond precipitation under intense pressure, is physically real and occurs inside ice giant planets. A nuclear detonation would be essentially seeding that process artificially, creating a localized storm of radioactive diamond formation that would produce flickering flashes of light visible across the solar system. There is no stranger sentence in science. A nuclear bomb detonated on Uranus would make it rain diamonds.